To combine all this together, my most successful technique was to attack the gradients first after calibrating all the images on each sub-exposure before stacking, because you can keep the gradients in basically one linear form rather than having your images travel over the course of, say, 4 hours and the angle of your light pollution changing in those images. When you stack those 4 hours of images together without getting rid of gradients, you end up with a nonlinear, almost radial gradient that'll be unique every time you're going to calibrate or to get rid of these, and it becomes a real pain. So I used MaximDL and PixInsight to get rid of some of these gradients. Actually, PixInsight has a great gradient removal program. Yeah. It has a kind of a tough learning curve, but once you get it, it works really well.
I was curious, how come you didn't use PI to do your mosaic stitching? Because it allows you to do that as well.
Because it would fail sometimes too on a 32-bit system. It worked way better on a 64-bit. And I was just using the program, so I wanted to stick with things I knew. So it came out fine that way. Still, I think, although PixInsight does a great job stitching, I still have better results using Registax and Registar. And I think it's, again, a level of familiarity with this program. Not to mention, I dropped $169 on it. I want to keep using it. So this is a single 20-minute exposure with the U16 again, and then after I got rid of the light pollution, it really pops out. Sure. So as I show you, the light pollution is very straightforward. It's all coming from one direction. This is due south while the object was crossing the meridian. That's that same region with the LIPUS. And so as I calibrated each image, the light pollution would change from this direction to that as it's going down across the sky. So I would use Maxim or PixInsight to basically attack this linearly using 4 points and a centroid. So it comes out pretty nice. I was completely unaware of this stuff at the bottom before I was working with this data. So switching from the 11,000, the ST11000 to the 16803 essentially doubled our quantum efficiency while working on these large frames. And we also changed from that wide bandpass filter to a 3 nanometer, which blocked a lot more off-band signal and made it a lot easier dealing with the gradients. So with our 19-degree field of view on the 110 millimeter lens, sky flats were pretty much impossible. But our best results were recorded using custom-built flat blocks. Also, we tried towards the end using the electroluminescent panels from, who is it? Yes, Allen-Tech Systems. They worked pretty good. This is the rough stitching together of our entire last mosaic before I blended all the segments together. And this is just straightforward stitching it together using Registar, and then doing the final cleanup and bending it back a little bit so it presents as a rectangular format. To give you an idea of how deep this exposure is, most of the faint nebulosity only out here only shows up in that radio image previously before. We couldn't find it anywhere else in all sky surveys or whatnot. So again, here's one of our favorite regions. And this is the entire final version over Dennis's house. Again, registered to the proper stars in the field. Gives you an idea of the perspective here. If if you go outside tonight and look outside right after sunset, Orion will be in the same position, although 25 degrees higher in the sky. But from here, our mosaic covers most of the sky that's straight up ahead just after sunset tonight. Now, what was interesting after this fact was putting this image together, it added a new level of interest of astrophotography, for me at least. It transformed into something beyond just making a big, gigantic, gorgeous image. When I started looking into what each of the objects are, essentially before after I had put this together, I decided I wanted to make a map where I'm plotting all the objects in the fields of view. And that opened a can of worms. So one of our earlier images with that Sharpless region, I had taken and started to plot out all the Sharpless objects and NGC 1491 over here, and whatever else I could find. But this little bugger resisted any detection anywhere. So this is what I was able to find by going through Aladdin and Sinbad and some of the common Sharpless objects. All the B numbers are Barnard Dark Nebula. Here's IC 361, which is a little open cluster. But this little guy here, again, I couldn't find it anywhere. The only reason I have it designated is so that I could get back to it. So I followed up on anything that I noticed in my images, and it's good advice for anyone. Once you take a picture, you always have that raw data to go back to. You can do a lot of science even after the fact. So my suggestion is to follow up on anything that you notice in your own images, and who knows, you might find something that you might have previously overlooked. And the worst thing that can happen is you become really knowledgeable about where stuff is in the sky. Here's an excellent resource for hunting mysterious blobs in our little images, which is Sinbad, and that's, here's the address here. Anyway, in the interface here, you can search your field by coordinates, which I found the most easiest. You know, just basically go, all right, what's this object over here? Type it in, and you can search by a radius, and it will give you, spit back out anything from any NASA satellites or even European observatory plots. I found it easiest to narrow your search down if you get too many hits. For instance, if you're looking for something next to M42, you're probably going to get a lot of hits. So if you do a 2-degree field of view, you can go down even into the arc minutes or even arc seconds to refine your search. I often use the POS2 red and blue plates for star charts on skymap.org to verify objects in our field. This is easily accessible online for free from skymap.org. You can go to any position, again, type in your right ascension and declination, and it'll zoom right into what you're looking for. This is that little group of stars, and you can't see it on this screen, but there's that nebulosity showing up around it. So, well, that proves to me that I wasn't getting clouds in that one image. And again, when I searched for this object by right ascension and declination, I couldn't find anything. I did expand my search a little bit, and it spat out this list of objects. There's often Tycho stars, IRAS hits, HD, that's the Henry Draper catalog, and a few other various surveys like 2MASS and a few other things. So plot around after you found your object in an Aladdin preview. Going by what I found for that particular object was IRAS 4, I'm not even going to read it because it's huge, a big IRAS number. Anyway, so then when I have this object, you can plot the area to see what Aladdin generates for what this object is. And this is, let's see, for the IRAS version here. It gives you a general radius, and then you can also look at the DSS preview. Again, here's those small stars, which kind of looks like a tiny version of Corvus. This is when, after that thing, following up on that object, I had my friend Sheldon shoot a really deep 8-hour exposure of this with our 12.5-inch f4 Newtonian and my QSI camera. Anyway, and it reveals some of the bow shock of hydrogen nebulosity in the region. And this is when we added color, so pretty much it's a hydrogen nebula. Here's some of the follow-ups on the stars in the vicinity, and it turns out that I believe that B2D star might be the precursor, or what's illuminating, this star right here might be what's illuminating the nebulosity around it, because it's a proper spectral class. Anyway, I had a friend of mine follow up on it, shooting it with narrowband filters, sulfur 2, hydrogen alpha, and O3, to see what else we could discover about it. There turns out to be nothing but hydrogen, maybe a hint of S2, which is only about 3 nanometers away from hydrogen alpha, which here's an animation too of the POS survey images going back from 1950, 1980s, and our final image. One interesting thing doing this too, following up on these stars, on these objects, is when you animate them, you start to see like some of these stars have proper motion. There's another one over here, and this one up top over here. All of these so far that I've found in this field happen to be known to have a proper motion. But it's pretty interesting to actually see that the sky can move over the course of your lifetime. With all of this stuff, I made notes, and I've been putting together a large paper to submit to a journal. Whichever I ever have time, I'll finish it up and send it in. But objects with IRAS designations actually don't mean that it has been studied in detail. As I mentioned previously, the IRAS satellite basically mapped the sky, and if it got a signal on something, it assigned it a number. When scientists and astronomers are researching different areas in the sky, they'll go back and go to the IRAS data or the Chandra, see if there's any images taken with that in the vicinity. So you can, even with small telescopes or even camera lenses, contribute big science to what's going on nowadays. And you can do it on the cheap, too. Another problem, though, that we've had is there's no one-stop shopping when there's researching astronomical objects. Sinbad does default to catalogs designations unfamiliar to most of us amateurs. You won't find many sharp list designations in this, but you will find obscure catalogs like that, the 2MASS or IRAS designations. So, but there are other resources such as in SoftwareBisque, SkyEsks, Professional, and other programs that draw from many different surveys, and often from not just U.S. centric data. So again, don't limit your search parameters, and also don't feel like just because you didn't find it in one search, try searching for the same subject in different ways. Just like doing a web search for a particular set of speakers that you're interested in. You want to read a review on that, you can type in the object in Google and find a review on it. But if you type in the object in a different way, like for instance, you want to find out if there's any complaints about a said product, you want to change your search parameters. Same thing with astronomical subjects. search for your object by the region, narrow your field, and also search in adjacent fields. Perhaps maybe the object you're noticing may have been something that's been moving for a long time. Anyway, until I get a copy of the SkyAxe, it was back to the books for me. Here's some of the databases that I have on hand with my fortuitous position at working at Sky and Telescope. Anyway, so after our initial search, we ended up following up these same fields with the 400 millimeter Pentax lens, showing you how deep we can go with twice as much exposure. This is the same field with 8 hours and a 3 nanometer filter. It shows you how deep you can pretty much go. Here's our little object here. Here's this is Auriga IC 405 and 410, or vice versa, and quite a few other sharpless objects. And buried in here, right here, that's I believe M38, the open cluster. And yes, it's M38. This is without stretching the data terribly deep. It gives you an idea of the entire field. Again, I would go into these closer up fields and research any of these little blobs that I would detect in these images here. This one over here is a planetary nebula named Touche with a long thing. But the point is that, hey, it was known and I was able to plot it on this. My goal eventually is to make charts that I can potentially publish in a book in the future for reference, so other people don't need to do this. Anyway, the point though is that it really added a new level of interest and reinvigorated my interest in astrophotography. Going beyond just taking a pretty picture and looking more into the science that can be gleaned for it, even if it's just, science for your own particular sake. You're not discovering something new, but you're furthering your own knowledge. It adds just so much more level of excitement to going out with the telescope each night. Here's a few more fields. This is up in the Auriga region also. This is a few IRAS nebulosity. And this little guy, I haven't figured out what it is yet either. I couldn't find this, nor there's something over here that you can't see on the dark projection monitor. Anyway, I would also follow up on some of these other objects with Sheldon using the larger 12-inch scope. Like this is SH2-227. And here's SH2-228. Some of our projects, Sheldon and I like to shoot things that, you can't find too many images online for. So it's a hit or miss thing, but again, it's part of the chase. Rather than yet another M42, we're starting to contribute images that you can find online that you weren't able to previously. Here's SH232, 235. Again, with the QSI. There's a few planetary nebula in this image, too. Right up over here. That's a PNG 173 and 173 plus 3.1, that little blue speck. Here's a IC 405. There's a popular object. Here's 410. And one of my particular favorites is IC 417, which I find interesting because there's these small reflection globules right next to the primary nebula of hydrogen. Here's the Fly Nebula, which is NGC 1931. And here's M38, closer up. And as you can see, it's surrounded by a lot of hydrogen nebulosity. Here's another large mosaic with the 400 millimeter lens, following up on our previous work in Monoceros. What I'm interested in this one is there's these this Beauchoc region in this area that I'd like to follow up with narrowband data or later this year. I have a friend of mine shooting that currently. And again, shows you how deep you can go with amateur equipment. So just because you don't have a giant telescope doesn't mean you can't look a little further than maybe anyone else has done previously. And again, zooming in on that region where I was able to find a couple of obscure objects, following up on that rosette image. This is the area that I was mentioning. There's these thin Beauchocs that I have a friend of mine shooting in oxygen 3 to see if that potentially might be a supernova remnant. Okay, so my advice is establish a project of your own for such as supernova searches, minor planets, or even expansive mosaics to add a new level of excitement to your hobby. The end result is usually the same, a great sense of accomplishment and increased knowledge of the sky. But above all that, have a lot of fun doing it. Any questions? Okay. The last half of it, we're mostly done with the 38 by 38 millimeter KAF 16803 CCD. It's 16 megapixels with 9 micron individual pixels.
You said you switched from one KAF sensor to another.
Yes. Previously, we're using the ST11000, which uses the KAI. It's the popular ST11000 had the what's that? 11 megapixel, 9 micron pixels, but it wasn't as sensitive as the 16803.
You can just swap them out in the same camera?
No, it was a different camera altogether. You had a question, Don?
No.
Okay.
I'm a great fan of pixel cloning,
Uh-huh.
and you can generate double the amount of pixels in half the size by cramming them into the same frame.
Yes, that's binning, right?
Binning, yeah.
Yep.
So it's a good.
Binning is useful when you're oversampling or close to that. For a wide field lens like this setup, you lose a lot of resolution. And as you can see, I was trying to extract as much as I can. And even at this image scale, we were doing maybe about 8 or about 9 arc seconds per pixel, which isn't high resolution at all. But when you bin those, you're getting up in the 20s, and anything below that would look like a star image.
I generally don't like the bin because some certain sensors, the horizontal readout register does not have the same size as the 2x2 bin.
Yep.
On the sensor.
Even in a larger image scale, when I'm shooting through a telescope, I prefer not to bin, especially for shooting color exposures, because you lose a ton of resolution, particularly in the blue, where you can get a lot of subtle shading in some of the nebulosity, like things with a little touch of reflection nebulosity will just get lost if you're undersampling compared to your luminance data.
Well, what happens is you truncate all the stars.
Yep.
And you lose color in the stars as well.
Mm-hmm. Okay. Yes?
So what program do you use for guiding the mount to the mosaic frames?
Guiding the mount. The mosaic wasn't guided with a program. It was using an old SBIG STV, which is a standalone auto guider. Doesn't plug into a computer at all. It's
You mapped out where the frames are going to be.
Right.
Where you're going to cover.
Uh-huh.
So the frame, when you had to move the mount from one frame to the next, what program did you use to designate where the mosaic targets were going to be in it?
The mount used was an astrophysics Mach 1. So literally, we could just, after it's synced, when one field was done, you could center on the next right ascension and declination, which Dennis had plotted the center of each of these fields.
How did you do that?
You literally just type in the go-to area. Oh, but how to plot them? He did that with an old map and the slide rule that you saw there. He's old school. Anything else? Thanks a lot for your time.